Thank you very much for the opportunity and for reading. Maybe a better title would be, did we pick the golden apple? In the sense, for undirected distances, you have this square root of 8 thirds where you can compute everything. But then after many years of attempts, any other value is not working. So after our first project on square root of 4 thirds, the natural question was, is it a miracle of this parameter or we can attack? And actually, as Ewan was saying, in this talk, I will try to convince you that there is nothing really special about square root of 4 thirds. It's special in the sense that it makes things slightly simpler where you are exactly at square root of 4 thirds. But we can generalize our technique to cover this range. And actually, all what I'm going to say, I'm expecting that it should be true up to square root of 2. But for technical reasons, we have to stop at square root of 4 thirds for the moment. OK, so what's the model that I'm going to analyze in this talk? So I'm going to look again at directed planar maps. So I will try to repeat most of the definitions, but I will speed up in the sense that you already saw them. So it's a planar map with an orientation of the edges, and these are cyclic in the sense that it has no cycles, no directed cycles. And it's bipolar if it is acyclic and there is only one sink and one source. So the planar map should look like something like that again. And for the moment, we restrict to triangulation in the previous talk, so all the faces are triangle. But later on, we will consider more general structures. OK, the goal for the first part is to introduce a natural one-parameter model of bipolar orientation that is in the gamma-LQG universality class for different values of gamma. OK, some models of discretization of gamma-LQG for different values of gamma. And one natural approach that mainly has been used in physics is to reweight the law of each map by some constant A to raise to some statistic of the map. And this statistic can be the number of spanning trees or many other stuff. So this is what we're going to do. And the way we do it is the following. OK, if you take two triangles next to each other, you get a quadrangle. You can bet in any different quadrangle, I will look at the case where the quadrangle is a 2-2 quadrangle in the sense that you have two left boundary edges increasing and two right boundary edges increasing. And I will say that an edge of this two triangle that is shared is right flippable if this edge is connecting the two vertices that are not the sink and the source of the face, and it's left oriented. OK, so why this? Because if I flip this edge to the right, I do not break the property of being a bipolar orientation. So these are exactly the edges that you can flip from left to right in the map and preserve the fact that you are still a bipolar orientation because you did not create any oriented cycle and you did not create any new sink or source. OK, let me give you an example. For example, here we have a map, and in green, I color these edges that are right flippable. So these two edges, if you flip them, you get again a bipolar orientation. OK, so given a map M prime, there are a set of edges that you can right flip, and I will denote by R this set of R flippable edges. And I'm allowed to flip them or not to flip them. For example, in this case, I just flip this one, but I did not flip the other one. So R is the set of all possible flippable edges on the right, and S is the one that I actually flipped. Yeah.
Couldn't you create some cycle if you flip, that goes through this?
No, you cannot. There are some limitations. It's not obvious, but you can write a simple proof. And we introduced this model. So the probability to see a planar map M prime, random planar map with a set of edges that you have flipped, is proportional to a constant time to the number of edges that you actually flipped. And this is reweighting the law of the map, the marginal law of the map, by this constant, 1 plus A. OK, here there is a missing rescaling constant that is the same as here, to the number of actually flippable edges. So another way of thinking of this model is you sample the map according to this Boltzmann law, and then for each green edge, you flip it or not independently with probability A over A plus 1 is exactly the same model. Okay, so you have a planar map, some set is oriented, some set is you can flip. You choose if you want to flip them or not with probability A over A plus 1 or 1 minus A over A plus 1. Okay, now, once you have this model, you have a first orientation that was before flipping and a second orientation that is after flipping. So now, roughly speaking, you have a planar map with two orientations. And what we're going to declare is that a path is oriented in this map if it's oriented with respect to both orientations. So it's like, in spirit, like reweighting a planar map by two spanning trees. We're reweighting a planar map by two orientations. And there is a simple thing to do. It's just every edge that you flipped in the orientation, you just forget it because this one will be oriented in one way in a map and in the other way in the other map, so you cannot travel through it. So for the purpose of directed distances, it's exactly equivalent to take the map M prime minus S. And it's not too hard to convince yourself that the probability to see this map now is just a constant times, here there was the number of flip edges, that now is exactly the number of quadrangles. Because we started with a triangulation, we removed these edges, and we got some quadrangles. So another very simple way of looking at this model is planar map with triangles and quadrilaterals, and it's reweighted by the number of quadrilaterals, which is something that has been done for other models of planar maps. Okay, so this is our model. I'm fixing n edges, and the A is a constant. And okay, here there is a lot of numerology. I wrote down all the formulas that you will see along the way here. They're not very important, but if you want, they are there. So if you set gamma between 0 and square root of 4/3, and you define rho to be minus cosinus of this quantity, and you take A to be this ugly value, it's some number, then you can argue that a planar map M reweighted by this law with this exact value of A is in the gamma-Liouville quantum gravity universality class for gamma that we fix. So all my quantities will be fixed when you fix gamma. So all the quantity that I have along the talk are all determined once you have fixed gamma. So from now on, fix your favorite value of gamma between 0 and square root of 3rds, and we're talking about that value, for example. I want to stress that is in the gamma-LQG universality class with respect to undirected distances. So undirected distances in this map should rescale as distances in the gamma-LQG metric. And I will justify this claim a bit later on in the talk. Okay, any question about the model? Good. So now I have a few slides where I'm going to repeat what Hugo said, so I will try to speed up along the way, but if you lost something, it's a good time to stop me and say, okay, I didn't understand this step. So what you do is exactly the same. You have now a random model of planar maps. You take the Benjamini-Schramm local limit around a uniform edge of the map, and you get an infinite planar map. It's, again, acyclic. There is no sink and no source because they went to infinity. And there are some quadrilaterals, and there are some triangles. And I actually erased you can see still where I erase these flippable edges. Okay, once you have these, each vertex has the property that has a sequence of outgoing and a sequence of incoming. I will always take the rightmost outgoing or the leftmost incoming, as Ewan was saying. And doing these, always rightmost outgoing or always leftmost incoming, I find this boundary. And then I just cut the map here. And exactly as in the Ewan case, I will keep the edges on the right, and I will forget about the edges on the left. Okay, now you have this map, and you can define geodesics to infinity. In this picture, I decided to take the longest directed geodesics, but you can take the shortest one. And our goal is to define this Boosman function on this boundary. And I will label the vertices on the boundary exactly as before. So x0 is the first vertex on the root edge. You have x1, x2 to the right, and x-1 and x-2 to the left. Okay, this is the model, and again, the analog is this part of the plane that has been explored by a space-filling SLE kappa with the right kappa associated to gamma here. This depends. For gamma, exactly square root of 4 thirds was 12, the value, but it's going to change.
Can you maybe say more? I mean, I don't really understand how you get these paths there.
Yeah, sure. So that's a good point. Let me go back. So you start at this edge.
It is to understand, right? How you get this first path to infinity. That's clear. But these other paths, is this green or what color was this in the
these two you.
No, this I understand. But going back.
This one?
Yeah.
What I'm drawing here, and I'm gonna justify that this is possible, is for every point, I'm drawing the leftmost geodesic to infinity. Okay, I will show you that it's unique in a second, and I will show you in a second that they must merge. So the value that you see here, actually, I declare this value to be 0. And the value here is -1, because if I take the length of this path minus the length of this path is exactly -1. Okay? And if you take actually 2 points here, the length of the path up to here and the length of the path up to there, you take the difference is exactly the difference. Okay, let me make this more precise indeed. I will introduce the same notation. So LDP between x and y is the length of the longest directed path between x and y, and SDP is the same but for shortest. And XDP, where x can be either L or S, you choose which one you want to look at, between x and y is just a path that is realizing such a quantity. And an XDP geodesic from a point to infinity is defined as follow, is an infinite directed path starting from x, such that it has the property that however you restrict it between 2 points, it's a geodesic between these 2 points. So if you're taking the longest directed geodesic to infinity, like the one that I was drawing, this path has the property that if I fix 2 points along the path, this is exactly the geodesic among these 2 paths, and this is true for any pairs of points in the path. Any questions about these definitions? Okay, so the theorem that we have in the previous paper that do apply line by line to this new case is that for every point here, there is a unique leftmost geodesic to infinity. And if you fix 2 points on the boundary and you take these 2 leftmost geodesics to infinity, they must coalesce into each other. So if you take Px and Py, these 2 infinite orange paths, there is always a point Z that depends on x and y, where the 2 geodesics will meet and stay together forever. So this is the property that allows you to define the Boltzmann function in the following way. We declare that is 0 at 0, and the difference between 2 points is exactly the difference of the length of the path up to the coalescing point minus the length of the other path up to the coalescing point. Okay, this is how the Boltzmann function is defined.
So so is z sub xy finite almost surely?
Is finite almost surely, yeah. But depends on xy.
Do you mean that everything is almost surely here?
Yeah, everything is almost surely. Any other question? Okay, so now I can stop to repeat what we've already done and present the new main result. So in the LDP case, longest directed path, if you rescale the Boltzmann function by k in time and k to the -1 alpha LDP, where alpha LDP is this quantity, 1 minus gamma square over 4, quite a simple expression, you get that the Boltzmann function converges to the left to an alpha stable Levy process with alpha stability that value. So in particular, it's smaller than 1. But before, the positive jumps and the negative jumps of this Levy process were symmetric in the case of here, the hardest part, and you will see that this is playing a huge role, is that this Levy process is asymmetric. And it has a skewness, so a ratio between positive and negative jumps that is exactly minus beta, where beta is this quantity that is 1 plus 2 rho divided by 1 minus 2 rho, where rho is this cosinus. Again, some number. And in the positive part, we have something similar to before. Is again an alpha stable process, but in particular is a subordinator. So since we have a minus, it means that in the positive part, you have just negative jumps. And the two sides are independent. OK, and for the SDP case, is a similar story. You rescale by now alpha SDP. And alpha SDP is quite nice. It's just 1 plus now gamma squared over 4. And now you have that on the left, you have again an alpha SDP stable Levy process with now skewness beta instead of minus beta. And for the positive side, you have a slightly different story. You have an alpha SDP level Levy process with only upward jumps. And the main difference between left and right are due to the fact that on the left, we are not including the boundary things. And on the right, we do include the edges. But this asymmetry is important, should be there, because we expect that in the continuum, this is what's going on. It's not an artifact of how we define things. And again, the left and the right are independent. So roughly speaking, these are the generalization of the exponent that we saw before for any gamma between 0 and square root of 4/3. And again, I want to stress, I do strongly believe that these formulas are true up to square root of 2. We have a series of models that we are trying to analyze that should cover the full regime. But any of these models will require a lot of technical work. So we postpone it for the moment. Because the argument to get to this skin are quite technical. OK, any question about the main statement? OK, it has an immediate consequences in U and Stoke for certain model of finite bipolar maps now. In the gamma universality class, I don't want to enter in the details. Again, fix your favorite value there. There is a model that is Boltzmann type. We have the following, that the longest directed path between the source and the sinks scales like up to constant, like the number of edges, the size of the map, to 1 over the dimension of the LDP, where the dimension in the LDP case is this value here. And for shortest directed path, we have something analog, that the distance between the source and the sinks is upper bounded by the similar quantity, but where the exponent is now SDP. And OK, for some technical reason, for a lower bound, we can just show that there is a vertex that at least is as far from the source. So not very important, the exact details of these, but what you should keep in mind is the following, that dLDP and dSDP, this quantity, are the exact analog of the value d gamma that is widely open to compute for undirected metrics. So these should be exactly the analog in the continuum of the dimension of this directed notion of Liouville quantum gravity. So it's quite surprising that in one side everything is uncomputable, while on the other side it seems that you have this additional solvability that allows you to compute exponent exactly. And the formula are surprisingly easy, despite they come from a series of substitution that involves even the arctangent, the cosinus, and so on. OK. Any questions about the statement? So I'm going to do one thing, justify why these maps are in the gamma universality class, and then tells you where the hell these exponents come from. OK, the KMS procedure is quite similar to something before. Now you introduce a new parameter lambda, is this value here, some parameter. And you do the following. You start with an infinite boundary, where in the left you have the edges in blue. On the left you do not have the edges. On the right you do have the edges. And there is a marked edge in the middle. And now with probability 1 minus lambda over 2, you do the following operation. You just shift the marked edge to the right. With probability lambda, you grow a triangle, and you declare the new active edge to be here. With probability again lambda, you grow an anti-triangle. So this is a triangle with two boundary on the left and one on the right. This is a 1, 2. And the new active edge is exactly this one. And finally, we have these quadrangles coming from the flippable edges, where you have this Choo-Choo triangle that has been growing this way with probability 1 minus 3 lambda O. And if you do this with this exact value of lambda, and you iterate this procedure forever, the map that you get is exactly the map that we saw before, M0 infinity, this half-plane top map that is coming from the local limit of one model. And there is a very natural way of keeping track of all the steps that you're taking along the way in constructing this map through a two-dimensional random walk, where each of the 4 operations correspond to a two-dimensional step, and each step is taken with this distribution. So roughly speaking, you're just taking a two-dimensional random walk started at 0, 0, and taking one of these 4 steps with this probability, and you just iterate this procedure, and this is encoding all the exploration of the map. Any question about this encoding? OK, if not, you can compute. It's quite easy. You have a two-dimensional random variable, x and y. You can compute the correlation between x and y. And turns out that the correlation with all the parameters that I set is exactly rho, this value here. And this is equivalent to the statement that the planar map, the local limit of this planar map in this universality class, converge actually to gamma-Liouville quantum gravity in some sense that is called the pianosphere sense. If you're not familiar with this, let me give you, for example, a consequence of this. A consequence of this, using work of Ewan, Nina Holden, and Shin-san, and Zhanding and Ewan, again, is that if we take this m minus infinity, infinity, the local limit, and we look at a ball of radius n, the number of vertices inside the map is exactly scaling as n to the d gamma, which sounds like a good indication that your planar maps is exactly in the gamma universality class. And let me say that it's possible that in a few years, we're actually able to prove this kind of convergence because there is ongoing work of Nina Holden where they are really trying to develop how to go from this pianosphere sense to prove convergence with embedding. For example, it seems that they're able to do it for spanning tree decorated planar maps with the circle packing theory. And maybe not only that. And here d gamma again is this outer dimension, but we don't know this value. Especially we don't know it in the full regime there. Okay, any questions about this? Should finish at 11, right? Okay, perfect time. Now, I finally can tell you where these exponents are coming from. And why, to get this exponent, we had to develop a completely new technique compared to the square root of 4/3 value. And I will tell you why we cannot do the same. Okay, the fact that the increments are independent and they identically distributed on the left and on the right is exactly line by line the same proof that Ewan showed. So it's coming from this conditional independent of the left and the right of the Boltzmann map that you can push to geodesic slices. Okay? So this is exactly as before. What is left to do is to analyze the asymptotic decay of a step on the right and a step on the left. If we can understand how the tail behavior of these two random variables behaves, then we're done, because this is what is left to prove convergence to alpha stable Levy processes. So if we get the exponents of the tail of these two random variables, we get all the other exponents that we saw so far. So the key quantity is understanding how these random variables decay when they're big. Okay, where do the exponents come from? Okay, I will focus on the longest directed path case for technical reason is quite simpler than the shortest directed path. We need to do something more complicated for shortest directed distances, but the philosophy is the same in both things, and SDP becomes more technical. So let's call Fk the distribution of the steps on the left, and Gk the distribution of the steps on the right. And let's introduce, as in this case, the generating function or characteristic functions of this random variable. I will need to split the characteristic function of f in the positive part and the negative part, and this will play a key role. So f plus is the characteristic function of the positive part of the positive jumps of f, and the f minus is the characteristic function of the negative jumps. G is the characteristic function of the negative jump of G, but you can prove that deterministically G has only negative jumps. This is a deterministic fact. Okay, so you have these three characteristic functions now. And there is some well-known result that goes under the name of Tauberian theorem that, for example, let's focus on G. If Z is a random variable with low G, and you know that the characteristic function of G expands like that, is 1 plus some complex constant times t to the alpha, when t tends to 0 for some alpha between 0 and 1, then the tail of Z should decay like k to the minus alpha, where alpha is exactly the same exponent in the expansion. So these are well-known results. Actually, sometimes they have been used even more in enumerative combinatorics rather than the ring probability. But there is a lot going on like that. And actually, let me say, there is an analog version of this theorem if instead of the characteristic function, you're looking at the Laplace transform. The Laplace transform is just when you replace here Iy, where y is some positive number. So if you know that the Laplace transform of G expands like that, you get the same result. So it's enough either to get this one or this one. And then you're done. So our goal will be to get one of the two expansions. And then we're done using these Tauberian theorems. OK. So how do you do it? The first idea is you have this boundary, as we were saying before, and then you take one step of your KMS procedure, let me say this one, and now you have a second boundary. Like most of it is shared, but especially at these 2 points, you expect that the value of the Boltzmann function before taking the step and after taking the steps are a bit different. And what I mean by the 2 boundaries is the first boundary is exactly that one, the second boundary is that one now. Okay? So, but since the law of the map of the random walk is stationary, if you take a step of the walk, you can immediately prove that the law of the boundary is stationary. And in particular, the law of the Boltzmann function is stationary between the 2 things. But this KMS thing is giving a coupling between the first boundary and the second boundary. So using this coupling, you can write a terrible recursive relation for f and g. And then you convert this recursive relation for f and g into 2 functional equations for f plus, f minus, and g. OK, the equations are here. For example, these are the easy ones. The shortest directed path are more complicated. They're not the nicest one, but they are there. There are 2 equations. But now you are suspicious, because you have 3 unknowns and 2 equations. How do you solve a system of 2 unknowns, of 3 unknowns and 2 equations? You don't solve it usually. And indeed, you don't solve it. But in the gamma equal to square root of third case, we have a miracle. That you can prove that the jumps on the left and on the right, by some symmetry argument, they must have the same positive jumps and the same negative jump. So you recover a third equation that is just this nicest equation ever, f plus is equal to f minus. So you now have 3 equations, 3 unknown. You
have an f that's like a sum of the f plus and f minus.
Exactly. F is just f plus plus f minus. Thank you. OK, what you do once you have this additional relation is exactly what Ewan was saying. You kind of expand like that. You plug in the expansion in this terrible equation, you start to equate exponent because there are factors that are involving the exponential. And these are actually what are determining the actual exponents. You do some stuff like that. You take your 3 pages of computations. But there are 2 issues. First of all, for general gamma, this equation is gone. And in any case, even if we would be able to get a 3rd equation, we know that this methodology can only spit out rational exponent. For some reason that I cannot really explain up to the end, when you do this equating exponent between the thing, the only exponent that you can get are rational. But we want a continuum interval. So these kind of techniques will never manage you to get the full range of gamma between 0 and 4. So we had to develop something new. And the new idea is the following. So there are 2 main ideas. I will not tell you anything about one, and we'll tell you mostly about the other one, because the second one is more or less a complex analysis trick, and I think it's the right conference where to speak about complex analysis. So the first trick is we look at a 3rd interface. So there is the right interface, the left interface that was giving an equation. We cook up a 3rd interface, and we get a 3rd equation, believe me. There is a way of cooking up a 3rd interface and get an additional equation. So now we have this new equation. We have 3 equations, 3 unknown. You start to believe, OK, maybe we are in the right place. What you do, you compute f plus and f minus in terms of g using the previous 2 equations that were in the box. And you substitute this expression in the 3rd new equation. And you end up with something like that, which is nice because it's a complicated equation, but there is only g now. OK, you're happy, but when we saw the first time this equation, we were not super happy. And the reason is, in this equation, there is both g of t, but there is also g of minus t, which it's not too hard to prove that g of minus t is just the conjugate of g of t. But this is a complex number. So roughly speaking, you have a polynomial in z and z bar. And this does not determine the value. There are multiple solutions to this thing. So how do we do it? Our goal now is take this equation and get an expansion for g of t. If we do that, then you plug in back and you get expansion for f plus and with f minus. You run your Tauberian theorem, and you're done. Right? OK, how do we do that? OK, if you set epsilon t to be 1 minus gt, with a bit of work, but not too much work, you can show that this equation forces what is the limit of the argument of epsilon t when t goes to 0 from the left and when t goes to 0 to the right. OK, so this equation, in some sense, gives you a regime for the ratio between the imaginary part and the real part of epsilon t. And so it's going to give you this result that the argument of epsilon t when t decreases to 0 is going to be converges to minus theta, where theta is some explicit number. Again, you have to do all the chain of substitution, but this is just a function of gamma. And on the negative side, you get this other angle. OK, but what do you do with that? And here we were a little stuck for a while until when we thought about the following trick. The idea is use complex analysis. So you know that actually epsilon is well defined in the full upper half plane. And actually this function, epsilon, is quite nice because you can prove that in the upper half plane is harmonic, is holomorphic, and extend continuously to the boundary. So what we know at the moment is the following, that the map is mapping the upper half plane roughly inside this cone where the left boundary has been mapped to some ray of angle theta, and the right boundary has been mapped to some ray of angle minus theta. OK, we cannot argue a priori that the full plane is mapped inside this cone, but at least we can argue that the image is in the right part of the complex plane. So the imaginary part of epsilon of z is non-negative. Okay, now you have this. And let me give you an heuristic on why this is a good news. Okay, this is what we have from the equation. And now remember that our goal, epsilon z is 1 minus g. And our goal is to prove, to run the Tauberian theorem, that more or less this function is some constant times z to the alpha for some alpha greater than 0. This is our goal. Can you do it? Okay, assume you know this. Does theta determine alpha? Okay, actually, it's not too hard to do an heuristic and get what should be the value of alpha. You just plug in epsilon equal z equal to t and z equal to minus t, which is right and left boundary. We know that it's a constant t to the alpha or a constant you pick up this rotation factor from the negative side, t to the minus alpha. And if you write your constant as some radius times e to the I theta, eta, your constant, you write it like that, you get these two quantities. But now you know that eta must be roughly minus theta plus the pickup of the period of the exponential, and pi alpha plus eta should be theta plus some other mistake, m prime. Okay, you do the algebra and you get that alpha should be exactly 2 theta over pi, but now theta was just a function of gamma, so you computed alpha. And actually, it's not too hard to rule out the n, because a priori you can prove that the exponent should be between 0 and 1 with some argument. So we have now at least heuristically, this only knowing the direction is enough to get what should be the value. And actually, let me claim this is the exact value. So you plug in now theta equal to our tangent of lambda, you substitute lambda, you substitute rho, you get gamma. And this simplifies a lot. And actually, you get the expression that I told you, that alpha is just 1 plus gamma square over 4, or 1 minus gamma square over 4 in the case of SDP and LDP. OK, but this is no sense, because I just end wave. How do you make this rigorous? OK, the idea is, again, I'm going to use complex analysis. So how do you do it? So our goal is, again, it's not really needed to prove such a strong thing. I told you, if you have it for the Laplace transform, we are happy. So let's say be modest and say, OK, I'm going to try to prove it just for the Laplace transform. I want to prove that epsilon iy is some constant time y to the alpha, where alpha is the value that we computed before. OK, if you take log, and remember, the real part of epsilon is non-negative. So I can take the branch cut along the negative axis so that this remains holomorphic. So what I want to do is kind of showing that the log of epsilon iy minus alpha the log of y is of constant order. If I know that, then I have this. So let me take this and be very optimistic. I just set a z to be iy. I do substitution, and I get that I want to show that log of epsilon z minus alpha log of minus iz is roughly constant. But again, we are happy if we can prove it just along the axis. OK, so our goal now is to study this function. So we take this function, and we want to study this function in order to get this. OK, so our function is log epsilon z minus alpha log of minus iz, and z is in the upper half plane. And again, with some properties of epsilon z, you can prove that this function is actually holomorphic in the upper half plane and descend continuously to the boundary. Let's write it like real part plus I imaginary part, where u is the real part and v is the imaginary part. So U or V, in particular, are harmonic conjugates. And since this map extends continuously to the boundary, also the positive and the real and the imaginary part, they do extend to the boundary. And now the first observation, naive observation, is the following. If I take the real part of this function and I plug in Iy, since I cook it up in this way, I get that is exactly this function that we want to prove that is of constant order. Remember, if I'm going to prove that when y tends to 0, this is going to converge to a constant, we're done. How do you do it? Here, the miracle is you kind of start to guess that if you have information about an harmonic function on the boundary, you might get information about the harmonic function on the vertical line using these Poisson integral techniques. And this is exactly what we do. So the idea is look first at the imaginary part. So the imaginary part along the boundary can be computed explicitly. It's just this function. But since we cook up things in the right way, we know that this is going to 0 because it was exactly the result that we were able to determine using the equation. So the equation is telling you along the boundary, the imaginary part of V is going to 0. So it's a very nice function. And actually, it's continuous along the boundary. This is something that I cannot explain, but using geometric argument about these directed distances, we can argue a priori that Vt can grow at most as square root of t. Okay? You have a singularity maybe at 0, but at most is of this type. But still, the function is continuous. OK, now we're in business, almost. And the reason why we are in business is because we're going to write V of z using the Poisson integral as an integral that depends only on the boundary, V of t. OK, it's not exactly immediate. And the reason why it's not exactly immediate to do it is because we have only an understanding of d of t close to 0 instead of having an understanding of v of t along all the boundary. So you have to be a bit careful when you do these Poisson integral techniques. But with a bit of work, using this expression and some estimates, we can prove, combining this result and this result, that the gradient of v along the vertical axis at most can explode like 1 over square root of y. Okay? This is really using the information that you have on Vt, that is going to 0, this bound, and this Poisson integral estimate. It's probably 2 pages lemma. But when you see these, you're very happy. And the reason why you're very happy is because now you remember your Cauchy-Riemann equation that are going to tell you that the modulus of the gradient of u is actually the modulus of the gradient of v. But if you now take ui y1 minus ui y2, it's quite easy to bound. The difference is just, at most, the gradient of u integrated between y1 and y2. But the gradient of v of u is exactly to the gradient of v. And we have a bound on the gradient of v. So if you have this bound, you plug it in. And it's going to tell you that uyI is actually a Cauchy sequence. But if uiy is a Cauchy sequence, then this function is converging to a constant. And now you can plug in this into your Tauberian theorem. You get the exponent. We already computed what is the magic value of alpha heuristically. And you have a full proof. That's how the exponent come out. Thank you very much.